Humans have toyed with flight for a couple centuries, but nature has been doing it for millions of years. Fossil records suggest that primitive insects were flying 300 million years ago, and yet the concepts of flight are even older than this. In many ways, swimming is nothing more than flying in a much denser fluid. Swimmers on our planet have been mastering the art of underwater flight for countless generations. It's no surprise that scientists and engineers want to study just how these animals propel themselves. After all, they've been practicing far longer than we have. What is surprising is just how mysterious the results have been.
People started looking at insects and whatnot. They looked at the bumblebee, which, if you've ever seen one, it's kind of pudgy for its size. It's a little ball with small little wings. And when engineers first used fixed-wing aerodynamic theory to predict how much lift these wings could generate, they found out that these wings were too small to generate enough lift to carry the actual bumblebee. So how can a bumblebee fly? And the same thing with Gray's paradox, which is the fact that if you were to tow a stiff, rigid dolphin through the water, you'd get a drag coefficient over it. And when you measure that drag coefficient over how fast you can observe them swimming, you'll find out that they're swimming much faster than you'd anticipate, and that the muscle density of a dolphin is much, much stronger than most mammals. So in fact, 7 times stronger than what human muscle could potentially do. However, that just seems kind of ludicrous, because other animals that would have evolved directly from the dolphin or into a dolphin, they don't exhibit that strength.
So what's going on here? We've all seen bees. They don't just drop out of the air. And while super-strength dolphins are entertaining to imagine, they just don't seem realistic. Something else must be going on. Something far more complicated and interesting. Something far beyond the reaches of classical theories.
Researchers now understand that the magic behind these high efficiencies comes from the fact that these flow conditions are highly three-dimensional, highly unsteady, and very few of the classical assumptions that were made back in the time of the Wright brothers are valid for these complicated swimming techniques.
They're using some type of unsteady aerodynamic or unsteady fluid mechanics in order to create a laminar flow around the dolphin's body as opposed to a turbulent flow around the dolphin's body. When it's a laminar flow, you can get much lower drag coefficients, and therefore you could be swimming much faster than anticipated.
For example, if you look at the Navier-Stokes equations, kind of the fundamental equations of motion for fluid mechanics, the unsteady term is often set to 0 because it's negligible in a lot of cases, like steady airflow coming over an airplane wing. But in the case of these complex flows that we're finding in nature, you just can't ignore that term.
I think the unsteadiness is a big part of it. There's been a ton of experiments with airfoils. If you take an airfoil and you just put it at incidence and you increase the angle of attack, at some point it stalls. You get separation off the backside of the airfoil and it stalls and you lose all lift. If instead you're unsteadily pitching it up and down, you don't. The leading edge vortex actually stays attached.
Whatever the cause, these animals swim with such ease and grace that many see them as role models, supreme examples to follow when developing our own propulsive technology. The propeller, for instance, has long been our ultimate propulsion machine, driving nearly all underwater vehicles today. But evidence suggests that, as far as efficiency and elegance go, swimmers in nature blow our current methods out of the water.
We look at our designs and they're extremely inefficient compared to what nature has come up with. And the reason for that is sort of natural selection, and they've had millions and millions and billions of years to evolve.
The suspicion is that if the propeller were the most efficient way of getting around underwater, then natural selection would have produced a few propeller-like animals in nature. And yet what we see is a complete lack of natural propellers in the oceans.
By all studies, for example, manta rays are considered to be about 95% efficient as best as they can tell, whereas the best propellers are only about 80-85%.
And it seems unlikely that natural selection just hasn't found the propeller, because it's found so many other effective ways of swimming, some of which are very complicated.
You can have jellyfish, which essentially squirt out vortex rings. You can have rowers that have lots of little legs that move, or hares
Yeah, subcraniform wiggle most of their body or undulate most of their body, but except for maybe like the anterior third or so.
Activate pectoral fins. You have caudal fin motion.
And then you get to tuniform swimmers, and that's like sharks, where it's mostly just in their caudal fin and sort of the peduncle, which is like the narrowing of the body shape right in front of your caudal fin.
There's sea snakes, lampreys. There's a whole huge variety of motions.
In particular, researchers at Princeton University and the University of Virginia are working to better understand the fluid mechanics of the manta ray. The manta ray is the largest of the rays, some with wingspans up to 25 feet and weighing over 5,000 pounds. Due to their huge size, only 5 aquariums in the world have them on display. Still, people travel for hundreds of miles just to see them in action.
So I had the opportunity to go down to the Georgia Aquarium in Atlanta and observe and take some video of Mandy, who is their, I would say about 6 foot wide manta ray that they have living in their aquarium with their whale sharks. So they have this tank that's actually in the Guinness Book of World Records. This is like the biggest aquarium in the world. It's about the size of a football field in general. And so when somebody caught a stray manta ray in a net, this was one of the places that they could send her because it's one of the few places that has a tank big enough to accommodate a manta ray. Oh, there you go. That's Mandy, like kind of rubbing up against the window. At one point, after she ate, she just kind of went into this pattern where she kind of swam around once, and then she would just, if this was her head and this was her tail, would just go into a series of like 3 barrel rolls, just up over end, like in a row, like, and with seemingly like no effort, just like woo woo woo, and then she'd keep swimming.
I mean, the reason I got interested in this was really, I went swimming one time at Coral Bay on the western coast of Australia, and that is a fringe coral reef. So one day we went out and they have a spotter plane and they find the manta rays, and then they drive the boat out there and all pile off and snorkel with the mantas. And it was really like, it was just the most amazing thing I've ever seen in my life. I mean, these animals are just spectacular.
When swimming looks so easy to them, it must mean that they're doing it really efficiently. It doesn't look like they're straining themselves. And it's graceful and it's agile.
They just, they were magnificent to watch, to swim. Lampreys and manta rays and a lot of the ray family are migratory, and so they have to swim long distances, and that usually means they have to swim efficiently. So it comes back to using this mixture of muscle motion and passive flexibility to produce a highly efficient propulsion mechanism. And that's the motivation right now, is to see if we can't translate some of those same ideas into a future generation of underwater vehicles.
One thing we want to do at this point is just recreate some simple fins of various shapes and sizes and actuation methods and put them underwater and see how they perform. And we can do this using images provided by the biologist on our team. We can use overhead photographs to trace out the planform shape and CAT scan images to get cross-section data, and just run an edge finding algorithm to trace out the edge of the fin. And we can import these points into CAD software like ProEngineer and trace out these wing models. We can also just use simpler geometries like an elliptical planform and a triangular planform, which is what we've been doing in the meantime to get some control measurements. Once the fin model is complete, we can take the negative of that 3D image, and then that gives us a mold. And we're actually using a 3D printer to print the mold. So basically a 3D printer is like a normal printer, but it uses a binding agent instead of ink. So it lays down a really thin layer of particles, then prints a layer of the binding agent, then lays another thin layer of particles down, and it repeats this over and over again until it's gone through every cross-section of the model that you designed. And at the end, all the particles that didn't get the agent will just brush off, and what you're left is this rapid prototype. Once we've printed all the pieces of our mold, we melt down a PVC polymer. It's actually the same kind that's used to make fish bait, those little jiggly worms.
So we just put it on a hot plate in a beaker. We made about 2,000 milliliters for the biggest fin. The mold was clamped together and had some Vaseline on it so that it was easy to remove after the plastic hardened. And then when it looks about right, we just poured it into the mold. You have to work quickly when you're pouring in the liquid plastic because it hardens very, very soon.
And we put in these aluminum rods while it's drying, which will later be used to actuate the fin.
But we have a triangular wing, we have an elliptical wing, we have different sizes of the elliptical wings.
We hook each one of these aluminum rods up to a gear in a gear train, which is powered by a servo motor. And each gear is offset from the one before, such that it sends a heaving traveling wave from leading to trailing edge on the fin. And what's more is the phase difference between the first and the last gear determines how much of one wavelength is present on the fin at any time. And that's important because different rays have different numbers of wavelengths present at a time. The gear train is mounted on a rig which is suspended from two parallel tracks that run the length of our tow tank.
Pretty much the towing tank is just like a really large fish aquarium, but it's made out of wood instead of being made out of acrylic or glass or whatever. And then a plastic tarp keeps the water in. And there's two long rails that run the length of this large rectangular box, on which we have four kind of low friction little carts that ride up and down these rails. And sort of these four carts, two on each of these parallel rails, support the weight of a carriage that drops down into the water on which the manta ray wing is attached.
So it was kind of hard to work over the water channel because we'd be fixing things on the fin and everything would drop in. And so it's like a 4-foot deep tank. And so getting things out was really difficult.
So yeah, it was pretty exciting when we finally got it all ready to go and flipped the switch for the first time.
So the first day that it started swimming was awesome.
The thing actually swam. fin was swimming pretty slow at first, but we streamlined it a bit, made some adjustments, and it's just scraping up against the side. Pretty soon it was going 40, 50 centimeters a second, which is right up there on the same order of magnitude as real manta rays. So we were pretty excited.
To figure out how fast the fin's moving, we used an encoder set up on an axle, and the wheel that's attached to the other end basically tracks the Pasco track, and it's connected to LabVIEW, and it can read how many clicks, and then from that we can figure out the velocity.
We can use these to quantify the fin's performance as we tweak different variables like amplitude of the fin's motion, wavelength, frequency, planform shape.
So, we should run different fins down there and see if any of them, given the amount of thrust that they produce or the speed at which they go, is there a correlation with the shape?
And from that, we'll be able to back out things like the screw hole number and the efficiency of the wings and how much power is being put into it versus how much power we're getting out of it to see what are the most efficient wings. And so this experiment here to measure the velocities that they're generating is sort of a first approximation to figure out, well, this one swims faster. And then we're going to take it up into the water channel and use PIV in order to quantitatively figure out exactly why.
So PIV, it stands for particle image velocimetry. And so what you do is you seed a flow, and it can be any flow, with neutrally buoyant particles. So as close as you can get it, you want particles that won't sink or float, and they'll faithfully follow the flow. So they're just neutral, they just do whatever the flow would do anyway. There are lots of different things to use, but we use hollow ceramic particles that are coated in silver. And so you just mix them up with water, add a little bit of soap, which keeps them from sticking together.
And you seed the particle, you kind of pretty densely seed the flow with these particles, and you kind of set your flow in motion, whatever it is. We'd be looking at sort of the wake downstream of a manta ray wing.
And these particles are reflective, so if you shine a laser beam on them, it's generally used with a sheet, a laser beam that you use a lens to move it out into a sheet, and they'll reflect the light, and then you take images. One way to do it is take two images quite close together, and then you can then correlate those two images and get an average velocity over several sections.
So you take your two different pictures, like picture A and picture B, and you chop them both up into kind of small grids. Generally what you get down to is each little box is 16 pixels by 16 pixels big. Then you run a cross-correlation algorithm. It's kind of, you do a Fourier transform, but what you're really doing is you're taking these two little 16 by 16 pixel pictures, and if you shift picture A in any direction and in any distance really, and then you put it on top of B, where do you get the best match? So then in each window you get one displacement vector, and so then what you get is you get a vector plot, and you get the velocity vector at each of these places where you had an interrogation area.
And there are also methods to do of volumetrics, so you can get all three components of velocity using this technique. And it's a very highly used technique. It's used a lot of places, a lot of people do it, and it's very effective for imaging or for calculating velocity fields, a larger flow, as opposed to just measuring one point.
Data collection has only just begun, and the research is still in its very early stages, so there's no telling what direction it will go. Luckily, far from getting frustrated, the researchers on board are only getting more excited.
I want to find a mechanism for actuation so that eventually we will end up with an underwater vehicle that will be able to swim underwater, maintain depth, and initiate manoeuvring.
And the application being an autonomous, unmanned underwater vehicle that could potentially be used for naval applications for a number of things, mostly sensing and studying the ocean.
Manta ray motion is a very quiet motion, and so there is interest in, you have a propeller or some sort of other sort of propulsive engine that submarines and boats use now, and they leave a huge signal behind them, and they're very noisy.
So you can imagine right now a little research robot goes up to a school of fish with its really loud propeller, and it just scares all the fish away, and it defeats the whole purpose. But if we had a quiet, uninvasive, fish-like research robot, then we would have much better luck studying the ocean and its inhabitants.
In engineering, a lot of your motivation tends to come from military, whether or not that's a great thing. But not only does it look really efficient, but it's also really quiet. And so, like a underwater military application, quiet is obviously essential.
I think a lot of times we look very hard for the direct practical application, but I think sometimes we do it just to learn about it.
My personal reason is I just like to figure out how things work. So it's not just like I want to build something that's more efficient, but it's like, man, how do they swim so efficiently? Like that's just sort of I'm just curious.
I think people are starting to realize that there's a lot we can learn from the non-human engineering that's going on in nature all the time.
They're huge, they're hulking, and they just sort of like bend their body and they turn and keep going forward. That's cool. How do they do that?
Again, I keep looking at the videos of the mantas and I'm saying, that's what I want, but how do I get that motion? And that's a big question right now.
As humans, we value our engineering successes. We see them as testaments to the intelligence of our species. Yet, there is an elegance among the swimmers in nature that far exceeds anything humans have designed. Perhaps only through a deep respect of that elegance can we hope to go further.